folks, so on page 1 of the notes, we've got even degree functions in the left column. We've got odd degree functions in the right column. So the difference between this top and this bottom graph is that this has a positive leading coefficient, and the bottom one has a negative leading coefficient. And up at the top, on Friday, we said that the leading coefficient is the coefficient of the term with the highest exponent. But I also want you to write that it tells us what the right arrow is doing. So what the right arrow is doing. So if my leading coefficient is positive, that means my right arrow is going to be going up. And if it's even degree, that means my left arrow is coming with it, going up. If the leading coefficient is negative, that means the right arrow is going down, and the left arrow follows it. So your leading coefficient tells you what the right arrow is doing. But then knowing what we know about even versus odd degree functions, we can figure out what the other side is doing as well. So folks, moving on to the right side, this is where we have our odd degree functions. And folks, remember that even degree functions, we've got the quadratic parent function that we can refer to if ever we get confused. You guys know from the last unit that a quadratic looks like a U going up and up. That is my easiest degree 2 polynomial. And down here they show that this is y equals negative x to the fourth, but we could just as easily say that this is y equals negative x squared, or a quadratic that has been reflected over the x-axis. So if you can't remember these key features, think about a quadratic and think about what its graph looks like and apply that to our polynomials. Same with odd degree functions. The easiest odd degree function that we have is y equals x cubed. The cubic function, which goes up on the right, down on the left. And then if I vertically reflect that, it's going to look like the graph that we see here. So odd degree functions, they do the little disco dance, and our end behaviors go in different directions. So next to even degree, over here, I would just draw up and up for even degree positive, because as we showed with some of those weird graphs on Friday, there could be a bunch of waves in between. For example, I could have something like this, boop-a-doop-a-doop. But we know that the end arrows are going to be going up. Same with even degree, leading coefficient negative. The arrows are going to be going down, down. We could have any number of ups and downs that happen in between those, but the end behavior arrow goes down. Now, odd degree functions. Oop, wrong arm. Cross him out. They do the disco dance. And which way they do the disco dance will depend on if the leading coefficient is positive or negative. Positive leading coefficient, the right arrow goes up and the left arrow goes down. If our leading coefficient is negative, then the right arrow goes down and the left arrow goes up. So the leading coefficient sign, whether positive or negative, tells you what your arrows are doing. Now on Friday, we did a lot of stuff on our calculators, which is all fine and dandy, but what we're going to be getting into is what do we know about these graphs based on just the equations without using our calculator and with using our calculator. These key features are going to help us graph. They're also going to help us with solving. And how many of you plan on going on to take calculus? Yeah, AP exam, there's a lot of stuff on there that they don't let you use calculators on. So some of this stuff will come to haunt you back or when you go on to take Calc 1. For the rest of you, this is going to help you get your bearings with what these functions look like. Now, before we talk about the end behavior, let's talk about the domain. What I love about the domain of all polynomials is that it is all real numbers for any type. All four of these have a domain of all real numbers. There's no restrictions on what we can plug in for x, and all the graphs are going to continue to go outward and outward, or all the way left and all the way right, giving us a domain of all real numbers. Now, the range for an odd degree function is all real numbers as well for both of these ones. because those graphs go all the way up on one side and all the way down on the other side, so the whole y-axis gets covered. The flip of that, whole y-axis gets covered by that one. But for the even degrees, am I going to have a range of all real numbers? Nope. So if you look at these two quadratics, I'm not going to get down here below that vertex, and I'm not going to get here above that vertex. Now, your range is going to be dependent on any kind of vertex type points that you have for the polynomial, but ultimately, you are going to have restrictions based on low points or based off of high points. So greater than or equal to a minimum or less than or equal to a maximum. But the domain is all real numbers for all of them, and we'll get some more practice in this unit with interpreting domain and range. You ready? Next, end behavior. Take a look at this notation. It looks awful. We've got the infinity symbol, which we have seen before when we were talking about interval notation in the last unit, but this notation simply tells us what is my function doing to the left and what is my function doing to the right. So by this part, I want you to write look right and look left. And also memorize. The notation seems pretty intimidating at first, but ultimately it says, what are my arrows doing as I go infinitely to the left and as I go infinitely to the right? So why do we care about end behavior? Ooh, let's see, I gotta do this so people at home can see it. Let's say I start up a business. When that business opens at day 0, have I made any money? No, I am in the hole big time for building the building. I'm doing advertisements, buying products, and then I start making money, and then maybe we have some dips in sales and do. If I am an investor, do I care about all the little ups and downs? I mean, maybe here and there, but ultimately, if I'm invested in this company, I want to know, is it going to end up trending up, or are we going to end up plummeting down towards debt or negative infinity? So end behavior doesn't care about all of these ups and downs. It cares about what my end arrows are doing. So folks, we're just going to practice reading this notation first. This says, as x goes towards infinity. So here's my x-axis. So as my x values go towards positive infinity, what is my function doing? Where is it headed? It's heading up towards positive infinity. As x goes towards negative infinity, so as we look left or head this way, what is my function going to do? It's going to keep going up towards infinity. So we look right, we look left. You can look left and then look right if you so desire. But ultimately, we care about what those end arrows are doing. Big mistakes that I see in this notation on the test. Sometimes students like to put equals here, like x equals infinity or f of x colon infinity. We have to have the arrows there to indicate movement, because I am moving infinitely to the right and seeing where this arrow is going. So make sure you've got this notation exactly as we start practicing it on the homework. And don't worry, folks, we're going to get lots of practice with both writing it and reading it. So let's go ahead and skedaddle on down to this one. As x goes towards positive infinity, so as I go this way, what's my function going to do? It's going down towards negative infinity. Next one, as x goes towards negative infinity, my function is going down towards negative infinity. As x goes towards positive infinity, so as I move in the positive direction on my x-axis, my function is heading up towards positive infinity. And as x goes towards negative infinity, we are going down towards negative infinity. Folks, I think before we go over that stuff at the bottom, we're going to just flip the page, and we're going to start seeing some of this stuff in action. Let's go ahead and start with end behavior. The notation is as x goes towards, I usually look left first. I usually do negative infinity first, but again, doesn't matter. What is f of x, or the function, doing? And then as x goes towards positive infinity, what is my function doing? So this is the skeletal notation that you will have to have memorized. This is what end behavior will look like for every single polynomial function. All we need to do then is describe what the function is doing, what those end arrows of my graph are doing. So let's try it. As x goes towards negative infinity, so as I go to the left, what's my function doing? Is it going infinitely up or infinitely down? Up. So as we look left towards negative infinity, this way, my function is heading up towards positive infinity. Then, as x goes towards positive infinity, what's my function or the graph doing? It's going up towards positive infinity. Is the degree even or odd for this one if my end behavior goes like this? Even. Question?
Can you zoom in?
Yes. So this would be even, and you can make a note that it's even because they go in the same direction. So even because same end behavior direction. Same end behavior direction. What about the sign of the leading coefficient? Or what is my right arrow doing? The right arrow is going up, which means we've got ourselves a positive LC, or a positive leading coefficient. Now, we don't know what that exact number is, but we do know that it is positive. Any questions so far? Let's try the next one. Let's practice writing that end behavior notation again. Oh, and actually, before we do that, as I mentioned, it doesn't matter what order these two blocks are in. So I could have this be switched with this. So I don't care if you look left towards negative infinity or look right towards positive infinity first. Just make sure it's paired with the right stuff. If you want to make sure it's consistent with what's on the answer key, look to the left first. So let's take a look at this one. And let's practice writing that skeletal end behavior notation. As x goes towards negative infinity, what's my function doing? What is it approaching? And as x goes towards positive infinity, what is my function doing? Take a guess. See if you can fill in what f of x is approaching for that one. As x approaches negative infinity, what is my function doing? As we go this way, our function is going up towards positive infinity. So positive infinity in that slot. As x goes towards positive infinity, so as we look to the right, as we're going in this direction, what's my function going to be heading for? Negative infinity. Negative infinity. All right, folks, what about the degree? Since my arrows are doing this, is it even or odd? It's odd. It's doing the little dance. So I would just make a note that it's odd because of different end behavior direction. So different end behavior direction. What about the sign of my leading coefficient? What's that right arrow doing? It's going down towards negative infinity, so my leading coefficient is negative. Down at the bottom, where we have some space, let's just travel down here. I want you to go ahead and write the notation. Just write that skeletal notation again. Practice it. See if you can do it without looking at the problems above. How do we look left? How do we look right? What does that notation look like? That's what it looks like. So that is that end behavior skeletal notation. And then all you have to do is figure out what the function is approaching by looking at those end behavior arrows. It's kind of weird. You'll get a lot of practice with it in the homework, but what I would do is I'd look at your notes for the first couple of problems, and then I would try to do the next two without. So folks, let's go ahead and flip back to this page, because not only does the degree, even or odd, tell me about the end behavior of the function, it also tells me about the number of solutions. So skedaddle on up here, and it says the degree of a polynomial, highest exponent, tells us how many roots or solutions the function has. Next to roots and solutions, I want you to also add zeros, which you can write OS or OES, fun fact, and x-intercepts. Now, all four of those terms, x-intercepts, zeros, roots, solutions, they mean exactly the same thing. Now, I remember when I first started teaching Algebra 2, I was like, that's dumb. Why don't they just pick one? And I still sometimes feel that way. So let me give you the lowdown of why we use different descriptions here. Solutions, we use a bit more in the next unit when we start solving algebraically. It's like, yeah, the solution, the answer to the problem, the answer to the algebraic equation. Roots, we tend to use a little bit more in physics. How many of you plan on taking physics at some point? Oh yeah, trajectory. So we have a cannon, we launch something into the air, and then it hits the ground. So if that goes in the shape of a quadratic, where it starts and where it lands, those are the x-intercepts of that function. So a lot of times when we're talking about stuff hitting the ground, we tend to use roots as the descriptor. Now, zeros and x-intercepts more go together because it's more about the graph side of things. Remember that x-intercepts are a number and zero. X-intercepts we can see clearly on the graph where it's hitting the x-axis, but zeros in a table of values is where our y values are hitting zero. So they all mean the same thing, and I would maybe put an important box around this. All of these are synonymous, and my goal is to get you comfortable with all four of those words. So going back to degree, and this will be helpful once we start solving algebraically and we aren't looking at a graph, your degree can give you an idea of some key features about the x-intercepts or the zeros. So let's go ahead and skedaddle on down here. Even degree polynomials have an even number of x-intercepts or an even number of roots. So even degree polynomial, even number of roots. solutions, zeros, or x-intercepts. Whereas odd degree polynomials have an odd number of roots. Let's write one there. Odd number of roots. So even degree, even number of roots, odd degree, odd number of roots. So 4 is even, 3 is odd, 2 is even, 1 is odd. What's 0? Is 0 an even or an odd number? It's an even number, so something to keep in mind, because as we see in this first graph, if I asked you how many x-intercepts does this graph have, how many times is that graph hitting the x-axis? It's straight up not hitting the x-axis. So this has 0 zeros or 0 roots, but I want you to add the word real. Whoop, real. Let's try that again. And put a little cloud around that. That descriptor is going to become very important as we move into the next unit, because real solutions are the ones that we can see. Later we find out about imaginary solutions, which are algebraic solutions that we can't graph on the real coordinate plane. So don't think about that right now, but this graph that has no real solutions probably has some complex ones. So it is important that we specify it probably does have solutions, they're just not real ones. Now on the next graph, how many times is this hitting the x-axis? Uno, dos, tres, cuatro. 4 solutions, 4 x-intercepts, 4 zeros. So even degree, even number of x-intercepts. Now for the odd degree ones, 1, 2, 3 x-intercepts. Odd degree, odd amount of x-intercepts. This one has 1 x-intercept. Odd degree, odd number of solutions. This correlation, again, becomes very helpful when we maybe only have the graph or we only have the equation and we're not quite sure what that graph looks like. So it will aid us in our solving stuff later. Turn the page. So let's go ahead and see how many real zeros we can see on this graph. 1, 2, 3, 4, 5, 6. 6 real zeros. This can also be helpful because remember when we were graphing on Friday on our calculators? Let's say you had an x-intercept at like 20, 0 or something beyond the scope of your calculator window. If you're looking and you're like, this odd degree function has 0 real solutions, that should put it on your radar like, oh, there probably is one since 0 is not an odd number. We just maybe can't see it. So this correlation is going to be something that helps us to make sure we didn't goof or miss one of the x-intercepts. So then what about over here? How many x-intercepts does this have? 3. We are hitting the x-axis 3 times. Now, your zeros or your x-intercepts are a number and 0, but your y-intercept what's the general format of the y-intercept? It's 0 and a number. Now, y-intercepts, they're not as, considered, I guess, when we're talking about solving. But for graphing, just like with lines, the y-intercept is usually a nice, easy point that we can find because we can plug in 0, which is a nice, easy point to plug into our equation, and that will give us some output, which is the y-intercept. So just looking graph-wise, where does it look like our y-intercept is? It looks like it's at about 0 and negative 0.8. An approximation. Now, I know I've said that normally we don't love using decimals on stuff because we want to be exact, but We are going off of an inexact graph here. So negative 0.8 is good. Negative 0.9 would be fine too. So give yourself some leeway as you are checking on the answer key. Just as long as it's close, that's good enough for me. What about my y-intercept for this other graph then? 0 and 1, 2, 3.2-ish. And that's just another good, easy point that we would be able to graph or swoosh through. Folks, let's go ahead and take a 1-minute break before we move on to the next problem. Yes? I made this place a little better. You can just have a new one. Yeah.
Oh wait, no, I found it.
Have to.